Okay, welcome to part 2 of the practical. What we did in practical 1 was we analyzed skin fold data, a multivariate data set, using the twin method to decompose the phenotypic variance into sigma A, sigma D, and sigma E, 4 components, ADE components, sigma A 4x4, sigma D 4x4, sigma E 4x4. We also tested a specific hypothesis about the decorrelations. Turned out they were all equal to 1, and that has a meaning. Namely, that means that the dominance genetic effects are common to all 4 skin fold measures. What we're going to do now is we're going to continue with part 2. I'm going to share my screen briefly, the workbook. So here it is. This is part 2. We've just done part 1 in the first part of this practical. So what we're going to do in part 2 is again carry out multivariate twin modeling, but we're also going to fit the independent and common pathway model to the data. Those models were explained in the previous PowerPoint presentations, but I'll go over them again here briefly. What we're going to do is read the data into R, so you can see on the left hand side, read the data into R, create the MZ, DZ data frames, calculate as always descriptors and correlations. Then we're going to fit the saturated model, I think, and then the ADE model. We're going to test for the significance of D, and then we're going to continue with the AE independent pathway model, AE common pathway model. So that's the plan for this practical. I'll share my RStudio screen and start the practical. So when you do this at home, the first thing you're going to do is you're going to set your working directory. Yeah, because the data set called N twin data, I think N for neuroticism, because it's this about 4 neuroticism items. We're going to set the directory. I'm doing this on my computer at home. So onderwijs, it's Dutch for education, and practical V2, and this is the working directory. So that's what you first do. If you want to try this at home, that's the first thing to do. Next thing I'm going to do is I'm going to go to the workbook, and as in part 1, it's cut and paste, execute analyses, answer questions about what you see of what you've done. Okay, so step number 1 is cut and paste the code. What this code does is it clears the memory. It loads libraries that we need, OpenMX and the library psych. And then it reads the data, the N twin data, reads into a data frame called N4. Once we've done that, we create MZ and DZ data frames. Yeah, and you can see I'm creating the data frames, MZ, DZ data frames, using the function subset. It's not the only way to do this, but this is one way to do it. If you're not familiar with some subset or with any of the functions that you encounter in this practical, you should enter question mark subset return, and that will open a help page. Yeah, you could also Google it, that always works. Okay, so that's step number 1 is read the data, create the data frames. That's it. And straight away we use the function describe, which is part of the psych library, to get the summary statistics. Yeah, so the marginal summary statistics, the summary statistics pertaining to each variable. Okay, in case I forgot, what are the variables? They are neuroticism items. Yeah, so 4 items taken from a neuroticism test, and these items come with a 5-point response scale. So that means that for instance, I'm often nervous, and the 5 options are applies to me completely, to applies to me not at all. Applies to me not at all is 1, 2, applies to me completely 5. So it's a 5-point scale. Some people call it a Likert scale. From the summary statistics, you can see that it's a 5-point scale. If you take a look at the min and the max, yeah, so it goes to 1 to 5. You can see the means, the standard deviation, the range, the min and the max, and the sample sizes. So you can see here we have about 1,520. We have 1,528 MZ pairs, 1,277 DZ pairs. Now these data are ordinal. Yeah, a 5-point scale is not, strictly speaking, a continuous variable, but we're going to treat them as continuous in this practical. Yeah, this is not the best way to do it, but it's not very important for what we want to achieve in this practical, that is, expose you to multivariate modeling. In practice, you could consider treating the data as truly ordinal and using full information, maximum likelihood estimation method suitable for ordinal data. You can do that in OpenMX, no problem, but it takes a long time. Yeah, so it's, in this context of this practical, we can't sit around waiting for 10 minutes or 20 minutes for the solution to pop up. So that's why we're going to treat it as continuous. Bearing in mind that that is not the best way to do to obtain estimates. Okay, the next step is you take a look at the marginals. They all look okay. And then the next thing we're going to do is we're going to calculate the MZ and the DZ covariance matrix, or the MZ-DZ correlation matrix. Yeah, so that's what appears next. I've cut and paste the code. You can see I'm using core, an R function, and I'm printing the RMZS and the RMZD, which is the correlation matrices. Okay, these results are also included in the workbook. And then we arrive at question 2.1. Consider the twin correlations of each item, and remember that RMZ greater than 2 times RDZ suggests a ADE model. Yeah, so that's a rule of thumb. I should note that if the RMZ equals about 2 times the RDZ equals, then that is suggestive of an AE model. Okay, but let's take a look at the correlations in the output. So what correlations are we talking about? Item 1, MZ twin 1 versus item 1, MZ twin 2. Yeah, so that is that value. You can read it off of the table. My items, I'm going to call them item 1 to 4, but they actually have a different name. I forgot to change the name. They are items 4, 6, 7, and 10. The first item is item 4. So we're going to look at the cross twin correlation for item 4. That is item 1, and the correlation is 0.21. And in the DZs, it's about 0.10. So that's the first correlation. The second correlation is looking at item 2, which is called item 6, 0.33 versus 0.17, etc. So the idea of this question is note these correlations and try to decide on what model might be relevant, using the rule of thumb. Now, if you do this, you'll find the answer in the answer sheet, which you'll have at your disposal when you see this. When you do this, you can see that almost all the correlations suggest an ADE model, but the D is very small. Yeah, so we're going to model these data using an ADE model because the correlation suggests that D might be present. But on the other hand, 2 times the DZ correlation is almost very close to the RMZ. Yeah, so that means that it's going to be probably an AE model. Anyway, that was question 1, and we'll continue with question 2 in a minute. First thing we're going to do is we're going to fit the saturated model to obtain the maximum likelihood estimates of the covariance matrix and the correlation matrix. And we're doing this. You might argue, well, you've just seen the correlations. Why are you recalculating them in OpenMX? We're doing this because we need the likelihood function to compare the saturated model with the ADE model later on. So that's another reason. In general, if you have missing data or a covariance, you'd definitely use OpenMX to calculate the correlation or the covariance matrices in the MZs and the EZs, as we did in part 1 of the practical. Okay, so let's run the. I've cut and paste the saturated model. This should run. It runs, no problem. And then we'll continue with. As a check, take a look at the MZs and DZ correlation matrices. We know what they should look like. Yeah, so they should to make sure that everything went well in OpenMX, we can extract that information from the output. Yeah, so let's dwell on that for a second. What is the output called? It's called sat4a. Yeah, so that's the OpenMX output. And to extract information from that, I can use the $ and refer to objects. Yeah, and if you want to, well, one thing you can do, and I'll show you that at the bottom, you can enter fit sat4a, and it'll show you what objects it contains, and then you can take a look at what's in the MZ submodel, yeah, etc. And that's the way, using the $, that's the way I can access specific parts of the output. So that's what I'm doing here. So what I wanted to do, I want to see the MZ and DZ correlation matrices, and here they are. Yeah, so correlation matrix MZ, DZ, we've already seen these. Yeah, and you've already studied the twin correlations. Okay. Next thing we're going to do, in the saturated model that I just fitted, I estimated 4 means in the MZs and 4 means in the DZs. Yeah, so that is 8 means. The twin model prescribes, it's actually part of the model, that the means in the MZ should equal the means in the DZs. Yeah, so I want to test that because it's actually an important hypothesis. Yeah. So why didn't we do that in part 1? Just to keep the practicals doable within the allotted time. Yeah, so we're going to do that next, and I'm going to use the function OMX set parameter to create the equality constraints. Yeah, so you can see here, referring to labels, and these labels refer to the means in the MZs and the DZs. So B01 MZ is the mean of neuroticism item 1 in the MZs. B01 DZ is the mean of item 1 in the DZs. Yeah, 2 different labels. But if I give these 2 parameters the same labels, I'm imposing an equality constraint. And that's what you can see here. Once I've done that, I can run the model, and I can compare the model with and without this constraint using a likelihood ratio test. So that's what we're going to do next. I'll run this code, and a likelihood ratio test will pop up. Yeah. So the likelihood ratio test, if you know, let's suppose we want to carry out a formal statistical test, null hypothesis test. Then in this case, the null hypothesis is the means are equal. Yeah. I choose my alpha, let's say 0.01, and then I conduct the test. Okay, I get a test statistic, and if the p-value associated with that test statistic is smaller than my alpha, I will reject that hypothesis, and I will say the means are equal. Yeah, so that's the way it works. Take a look at the test statistic, 6.05. That's a log likelihood ratio statistic. It has 4 degrees of freedom, and the p-value is 0.19. So that is much larger than my 0.01. So I conclude that the means are equal. Yeah, and that is good because that is, as I mentioned, that is part of the twin model. If the means are not equal, you have a problem that you have to find out what's going on. Why would the means be different? Why would the means differ? Okay, go to question 2.2. Are the means equal in the MZs and DZs? Well, we just answered that question. And why are there 4 degrees of freedom? Why is the 4 degree of freedom test? Okay, why? Well, we estimate 8 means, impose the equality constraints so that they were equal, and that gave us 4 means. 8 minus 4 is 4, and that's where the degrees of freedom come from. Okay, next step is, you'll not be surprised, we're going to go from the saturated model to the ADE twin model. Yeah, it's just as this is the same model we fitted to the skin fold data. There is one difference, and I just want to mention that briefly here. First, I'm going to cut and paste it. Then once I've done that, I can refer to the code to point out that this part of the code, I'm specifying the sigma A 4x4 associated covariance matrix, sigma D, and the sigma E. Yeah, and you can see these are symmetric matrices. The covariance matrix is symmetric, and I've given the elements in these covariance matrices their own labels. Yeah, so if you take a look at sigma D, it has 10 labels. Why 10 labels? Because sigma D is 4 by 4. It has 4 variances, 6 covariances. So it has a total of 10 elements. And I've given those, each element its own label. Okay. Now, in the previous practical, part 1, we didn't parameterize sigma A, sigma D, and sigma E in this fashion. We used standard deviations and correlations. We did that because in that practical, I wanted to test a hypothesis about the correlations. That's the last thing we did at the end of practical part 1. In this situation, I want to test whether sigma D is 0 or not. And if you want to test a variance component, a single variance component, or variance components as a matrix, in this case sigma D, then you have to model it as shown here. Yeah, unconstrained covariance matrix with 10 elements. If you don't do that, then your likelihood ratio test will not necessarily be correct. Okay, so that I just wanted to mention that. I'm sure you've heard that before from other people. Brad Verhulst, who you have met or will meet, has a paper devoted to this issue in behavior genetics. Okay, so that explains the difference in parameterization. And what we're going to do now is just fit the ADE model. That runs, no problem. And we're going to go to question 2.3. Does the ADE model fit relative to the saturated model? So this calls for a likelihood ratio test, which you can conduct using MX compare. So we'll add that to the code. Here we go, MX compare, run. Okay. Degrees of freedom of 42. This likelihood ratio test statistic is 57.6, and the p-value is 0.05, 0.054. Okay, if you want to carry out a formal test, then you say you give your alpha, you state your alpha, and then you find out what the p-value is of this test statistic. If it's greater, then the model fits. Yeah. So in this case, we conclude if you want to carry out the formal test, you conclude this model fits adequately compared to the saturated model. When you, just as an aside, when you carry out multivariate modeling, yeah, this is 4 variables, not very large, but if you have a large model, say 8 variables or 10 variables, and you have large sample sizes, then overall goodness of fit tests often are significant. Yeah, so that should, I'm mentioning that because I don't want you to leave this practical thinking, oh, every time I evaluate a model fit, I have to use the likelihood ratio test. That is not the case. There are many ways to evaluate the goodness of fit using information criteria, likelihood ratio, but a host of other fit measures and indices that are used in practice. Yeah, so I'm not going to go into that. That's not the subject matter of this practical, but it's important to realize that when you do multivariate modeling, you will often encounter models that do not fit. Yeah, and it's not necessarily, that's not the kiss of death for the analysis. Yeah, often there's no reason to take the goodness of fit that seriously and just continue modeling. Okay, so we know that the model fits, and we're going to go to question 2.4. Use OMX set parameters to drop the D component. Yeah, and in the output and accompanying this question, I explicitly mentioned the labels. Yeah, so I want you to use those labels in the OMX set parameter function. I'll just show you what the idea was for that question. So you already know what the labels are: SD11, SD21, etc. Yeah. So this is what you do. You use OMX set parameters. The output of the ADE model is called fit ADE4V. And I'm referring to these labels of the SD matrix, setting them all to 0 and fixing them to 0. So they're no longer free, they're fixed to 0. So once I've done that, my model is ready to run because I've effectively removed the D. Okay, so we'll run this. And that's it. Didn't take very long. Question 2.5. Use MX compare to carry out the likelihood ratio test of the sigma D variance component. Do we need it in this model or do we not need it in this model? So obviously, as you can imagine, we're going to use MX compare. That is presumably nothing new, comparing the ADE model with the AE model effectively, because you've dropped the D. Okay, so it has a 10 degrees of freedom. Why? Because the sigma D had 10 elements, 4 variances, 6 covariances. Set them all to 0. So that is 10 parameters difference between the ADE model and the AE model. That's the background to the 10 degree of freedom. The p-value, my p-value, let's call it 0.01. And what p-value do we observe? 0.81. So that means that there's no reason to reject the hypothesis. And that means that we can continue with the AE model. Yeah. In this context, the D is obviously small if you take a look at the twin correlations. Yeah. So I'm confident that we can continue without the D. There's just one thing I want to say about this. In practice, if you carry out a test, I'm testing whether sigma D is 0, and I make the statement based on my results, we do not need sigma D is 0. Yeah. Then when you do that, you've got to bear in mind, you could be making an error. You know, maybe sigma D is present, but by coincidence or just a coincidental result, the p-value is larger than your alpha, then you're making the wrong decision. Yeah. And to get a grip on that, you can carry out a power analysis. That's not the subject of this practical, but that's important to bear in mind. Every time you carry out a test and you cannot reject the null hypothesis in this context, then you've got to ask, I'm getting rid of sigma D because it's not significant. Is that an error? You don't really know unless you carry out a power analysis. Okay, so we'll carry out the likelihood ratio test, and we can drop the D, and we'll pretend that that's okay. We won't worry about a possible error. Okay, the next thing we're going to do is we're going to take a look at the results of the model fitting. Yeah. So we're going to take a look at the correlations and the covariance matrix of A and E. Yeah, so we can see here in the output at the bottom of the output window, RA is correlations of A, SA is the covariance matrix of A, RE is the correlation of E, and SE is the covariance matrix. So SA plus SE gives us the phenotypic covariance matrix according to the model. Okay, go to question 2.6. And the question is, you can see that the A correlations are much larger than the E correlations. Yeah, so look at RA and look at RE. Yeah, you can see the RA correlations are clearly much larger. Does that mean that A makes more? Does that mean that A contributes more to the phenotypic correlations than does E? That's the question. Okay, answer the question in the light of the following code. So I'm giving you this code, and I want you to look at the code and answer that question. Yeah. So, in a nutshell, the RA correlations, the correlations in RA are all much larger than the correlations in RE. Does that mean that A is making a larger contribution to the phenotypic correlations? Yeah. And to answer that question, what we're going to do is we're going to calculate the phenotypic covariance matrix. That's sigma PH, sigma phenotype. And we're going to divide SA divided by sigma phenotype, SE divided by sigma phenotype, and those will give us the proportions that sigma A contributes to sigma phenotype, and the proportions that sigma E contributes to sigma phenotype. And these results are shown at the bottom here. And what we can see is, so what are the diagonal elements in the top matrix? Yeah, those are the heritabilities. The off diagonals are the contributions in terms of proportions of A to the phenotypic correlations or to the phenotypic covariances. So you can see they're all just under, say 0.45. Under that, you can see the contributions of E to the phenotypic correlations, and they're all larger than, most of them are larger than 5. Yeah, so that means that E is making a larger contribution to the phenotypic covariances than is A, even though the A correlations are larger. So don't be misled by A correlations. Somebody says, oh, the A correlation between height and weight is 0.9. Therefore, genes are the important source of covariance between height and weight. That's not correct, because it also depends on the heritabilities. Okay, that concludes the saturated model and the ADE model. And the next thing we're going to do now is we're going to move on to the AE independent pathway model. And I just want to remind you what that entails. I'm going to stop this screen share, and I'm going to quickly go to my workbook. So what we're going to do is, let's consider the matrix sigma A, 4x4 covariance matrix. Yeah, we just saw it actually in when we answered 2.5. What we're going to do is we're going to subject that covariance matrix to a model. We're going to test the hypothesis that there are genes that are common to all 4 items, and there are genes that are specific to each item. Yeah, and that model is called a common factor model, and it's depicted here in this slide shown on the right-hand side of the screen. There you can see AC represents the genetic effects that are common to all 4 items, item 1 to item 4. Yeah, so C stands for common, the common genetic influences. In addition, you can see A1 to A4. Those represent the item-specific genetic effects. Now, we have sigma A, and I want to model it according to the path diagram. And to do that, we make use of a parameter matrix LA, which contains the parameters A1 to A4. These, you can call these factor loadings, if you like, but the interpretation is regression coefficients, because it's the regression of N1 on AC. Yeah, so that's 4 regression coefficients. And we need a second parameter matrix called TA, and that contains on the diagonal the 4 residual variances. Yeah. So using those 2 matrices, the LA and LT, we can model the sigma A shown in this slide. Yeah. So if you don't know matrix algebra, that's not really important here. This is the way we're doing. We're going to specify LA and LT in the OpenMix script. Yeah. Before we do that, I just want to show you this. I want to show you this in action. Yeah, just using made up data. Let me share my screen. Go back to RStudio. Okay, so this is just a small illustration. What you see here is an LA. Yeah, it's 4x1. And then I'm creating a TA, which is diagonal. And the values shown here are just arbitrary values that I made up. And then I'm calculating the covariance matrix using my matrix expression, LA times LA transpose plus LT, plus TA. That is the model for sigma A. And if I run this, you can see the LA, the TA, the sigma A, which is the expected covariance matrix given this model and these parameters. And then I standardize that. And that's the last result is the standardized covariance matrix, the correlation matrix, based on this common factor model with these parameters. So this is what we're going to do with sigma A and sigma E. Okay. So I'm going to cut and paste the code. We're going to run the code, and then we're going to go to question 2.7. I should add at this point, this factor only has 12 questions, so we're over halfway. Okay, so here it is. Run the AE model. Okay, just briefly, just go through. I just want to show you this part of the code. What do you see here? Literally LATA, LETE, and also LDTD. So that might be confusing. What's D doing in this? All those D parameters are fixed to 0. So effectively, this is an AE model. Yeah, and if you scroll down a little bit further, you can see we're creating the sigma A, sigma E covariance matrices as we just illustrated. Okay, so we got the results. And the next thing we're going to do is we're going to answer question 2.7. Does the AE independent pathway model fit relative to the 4-variate AE model? Okay. So that calls for a likelihood ratio test using MX compare. Does the model fit? The model fits well. I'm not going to go into the p-value and all that because I've done that once or twice already, and I imagine at this point you know how to interpret this. There is a question. Part of the question is, why are there 4 degrees of freedom? Yeah, that's a good question. What is the answer? Well, consider sigma A. That's a 4x4 matrix. It has 10 elements. Yeah, so 10 elements, 4 variances, 6 covariances. But the common factor model has 4 factor loadings and 4 residuals. Yeah, so that's 8 parameters. 10 minus 8 is 2. So we get 2 degrees of freedom for modeling sigma A, but we also get 2 degrees of freedom, the same reasoning, for modeling sigma E. So 2 plus 2 is 4. That's where the degrees of freedom come from. Okay. The next part is, let's take a look at the parameters of the AE independent pathway model. This is important because the model fits. Yep, good. But we've got to make sure that the parameters are sensible. Yep, you might encounter negative variances or factor loadings that are almost 0. So we want to make sure that that is not the case. Or, it's just evaluate what parameters did we obtain from this analysis. Okay, it's just cut and paste again. The code is given. And what you see here are the values of T of LA, the additive genetic factor loadings. They all look sensible, about 0.4, 0.5. The diagonal elements of the TA matrix. So what are those? Those are the item-specific additive genetic residual variances. Yeah, and you can see they're all quite small. They look small. The next bit is the LE, the E factor loadings. They all look sensible, also 0.4, 0.5. And if you take a look at the TE containing the item-specific unshared environmental variance components, you can see that those are quite large. Yeah. Then I calculate the sigma phenotype, and then I calculate the proportions again that I just mentioned. Yeah. So I want to see what the contribution is, what are the heritabilities and what are the contributions of A and E to the phenotypic correlations. We've already seen these results actually in the previous result, in the previous model. So there's nothing new there. Let's answer question 2.8. Consider the A and the E residuals. With respect to the item-specific A and E effects, what would you conclude? Bear in mind that the E residuals include measurement error. Yeah. So what I'm trying to get at here is you can see a very clear difference in the magnitude of the residuals when you compare the A residuals with the E residuals. The A residuals are tiny relative to the E residuals. Yeah, so that is, let's take a look at the first item. The A residual is 0.24. The E residual is 0.59. Yeah, so that's, what is it? Almost 20 times as large, about. Yeah, so why is that? The answer to this question, I'm already giving you a hint in posing the question. The unshared environmental item-specific effects includes measurement error. Yeah, so that means that all the measurement error that characterizes item 1 will be absorbed or included in that term. And I think that's the answer to this question. Yeah, why are the E residuals so large? Because they include measurement error. So you at this point, you might say, okay, but that means that the reliability of a single item is not 1, because reliability 1 in psychometric terms would mean that the reliability is 100% would imply no measurement error. Yeah. So this means that a single item is characterized by, you can do the sum in terms of calculating the proportion of variance attributable to specific E. I'll show you that in a second. But that means that the item must be characterized by a good deal of measurement error. Yeah, and that's correct. Yeah, because individual items in a test are generally characterized by a lot of measurement error. The reliability of an individual item could be 10% or maybe 20%. Yeah. So in psychometric tests, you don't have one item, you have say 20 items, the fact that the items individually are unreliable, it's not a big deal because the sum score of all the items together, when you calculate the sum score of the mean, the error terms are cancelled out. So that means that even though the items might have individual reliabilities of 0.10, that low, if you have 20 items, the reliability, the sum score is going to be in the order of 0.8 because the error averages out. Okay, that's just a little bit of psychometric background. Okay, reporting results. The next part of this, practical involves arriving at a representation of the results. In the previous practical, we discussed the path diagram with standardized parameter estimates. Yeah, easy to interpret. That is one way to represent your results in a user-friendly way. In this part of the code, we use code to create a bar chart. And I'm not going to run the code. I'm just going to show you the bar chart to show you why this is, why I call this user-friendly. Yeah. So what it does is I'll have to stop this share, go to my, okay, what you see here, the code is shown here, it's in red. I'm not going to discuss code because I don't, Dirk made this and I'm not familiar with the ggplot2 function. Personally, I would use a different function. Dirk made this and I'm not going to cut and paste this code. You can do that for yourself. Presumably you've already done that. This is the figure it creates, and that's what I want to show you. A user-friendly representation of the variance decomposition of the 4 items. Yeah, and for instance, you can see directly from this figure, the dark purple, I think the purple, that is the unique environment, and unique environment in this context means the item-specific variances. You can see they're quite large, and you can see that the unique item-specific A's are relatively small, with perhaps the exception of item 2. So this is like a path diagram with standardized parameter estimates. This is a representation which is user-friendly, something you could put in your paper to send off to a journal. Yeah. So it's important to think about, you're doing modeling and you understand what you're doing and you get all these results and all these tests, but ultimately you've got to think about, how do I communicate these results to the readership of your target journal? Yeah, so that involves thinking about, how can I represent the results graphically? And that's what you see here. Okay. I have to go back to the R Studio. Okay, so that is the common pathway model. What we're going to do now is we're going to continue with the, sorry, that was the independent pathway model. Now we're going to continue with the common pathway model. Okay, I stopped my share again, sorry. I should have stayed in my document. Okay, so we're going to fit the common pathway model. I just want to remind you what that is. Take a look at the figure on the right at the top. You can see the independent pathway model which we just fitted. Yeah. So the results shown here are the path diagram with the parameters drawn in. I'm only showing the residuals for the first item just to avoid clutter. Okay. So this is the model we just fit. Well, the model we're going to fit next, the common pathway model, is shown under there. And what we're under this figure, this is the second figure, bottom right. What we're now going to do is we're going to relate the items, the phenotypes, to a latent phenotype called neuroticism. Yeah. So that part of the model is actually a common factor model applied to the items. That makes sense because the items were designed to measure neuroticism. Yeah, in a strict psychometric interpretation, that means that the scores on the items are directly and causally dependent upon the latent variable neuroticism. And that is what is reflected in this path diagram. Yeah. What do these items have in common? The latent variable neuroticism. That is the variable that influences all the items, according to the psychometric theory. Yeah. So what we're going to do now is we're going to fit this common factor model and simultaneously carry out a decomposition of variance of A and E as shown in the figure. Yeah, so this is a common pathway model. it's a mediation model because the effects of A are mediated by the neuroticism, latent variable. Okay. Just one thing about scaling. So there's a technical issue. Scaling has been an issue throughout all modeling, all the previous univariate twin modeling, everything. There was always a scaling issue. In this case, the scaling issue is the latent variable neuroticism is not observed. It's a latent variable. So I don't know what its variance is. So I have to assign a variance to the latent variable neuroticism to be able to fit this model. Yeah, so I want to be able to estimate the sigma A and the sigma E, the variance components at the top. I want to be able to estimate the F1 to F4, the phenotypic factor loadings, and the residual variances, which are not shown in this figure. Okay, so to scale the problem, to scale the latent variable, I'm going to fix the variance of the latent variable to 1. So that means that the sigma A squared plus sigma E squared should add up to 1. And that constraint, that means that sigma E squared can be derived from sigma A squared. And that is shown at the bottom of the, just under the R code used to achieve this involves an MX constraint. And the constraint says sigma A plus sigma D plus sigma E has to equal 1. Now, that's a scaling constraint, and that's included in the model. You see the sigma D, confusing. Don't worry about it. Sigma D is fixed to 0. So effectively it says, in terms of the figure, sigma A squared plus sigma E squared is equal to 1. Therefore, sigma E squared is 1 minus sigma A squared. That's it. Yeah. Okay. So let's fit the common pathway model. I stop the share. Don't forget to go back to our studio. Cut and paste the code. Just briefly, so what we're doing, what you can see here, this LF contains the factor loadings F1 to F4. Then you can see SA and SE contains the variance components of the latent variables neuroticism. Then we have TA, TD, and TE. TD is 0. TA and TE, those are the residuals. And this part of the model is identical to the independent pathway model. The treatment of the residuals is exactly the same. And then you can see in this part of the model, I'm creating sigma A and sigma E, and then assemble the model and fit the model to the data. Yeah, so beyond this point, from here onwards, the code is almost the same in all analyses. Okay, so let's fit this model and see what the results are. Okay, model runs. It creates an error. Sorry, it's a warning message. Polite note from tryhard MX tryhard. Hessian not checked as model containing constraints. Ignore that. It's not important. Okay, so this model is run, and next thing we're going to do is question 2.9. There are only 12 questions, so we're almost there. The independent pathway model has 4 means, 2 times 4 factor loadings, and 2 times 4 residuals. The independent pathway model. Yeah, it has 4 A factor loadings, 4 E factor loadings. It has 4 means. It has 4 A residuals and 4 E residuals. Yeah, so that's 20 parameters all in all. How many independent parameters does the common pathway model have, and why is the DF in the comparison, the goodness fit comparison, equal to 3? Okay, so let's first do the comparison. This is question 10. Let's take a look at the likelihood ratio test. This is independent pathway model versus the common pathway model. And you can see the results at the bottom. Alpha 0.01, it's not significant. Okay, and the question is, why is the difference in the degrees of freedom? Why is this a 3-degree freedom test? That must mean that the difference in the number of parameters between the independent pathway model and the common pathway model must equal 3. Now we already know that the independent pathway model has 20 parameters. So how many parameters does the common pathway model have? Yeah, well, we can count them. We have 4 means. Yeah, that's characteristic of all these models. 4 means, 4 phenotypic factor loadings. That's 2 times 4 plus 4. Okay, then we have sigma A. That's plus 1. We're not counting sigma E because we derived that from sigma E is 1 minus sigma A, the constraint. Then we have 4 residuals A and 4 residuals E. So it's 4 plus 4 plus 4 plus 4 plus 1, 16 plus 1 is 17. Yeah, so we have 17 parameters in the common pathway model, 20 parameters in the independent pathway model. So the difference is 3. Yeah, you might ask, are these models nested? How do I know they're nested? Well, you can formulate the common pathway model using as a independent, you can formulate the common pathway model as an independent pathway model and introduce proportionality constraints. And that will give you a clear view of why they're nested. And I mentioned those, the proportionality constraints in the PowerPoint on this subject matter. Okay, so it's not a simple issue, but they are nested. Okay, so what is the next question? Next question is use the compare them. Use OpenMX, use MX compare. We've just done that. We've already established that the model fits. Yeah. So what we're going to do now, obviously, is we fit the model. We know it fits, but we want to take a look at the parameter estimates to make sure they make sense. Yeah. So that's the next step. It's just cut and paste, and we're going to take a look at the results. So what am I? So just briefly, the output is called fit AE4 CPM2. Yeah. So I'm going to extract from that output the bits and pieces that I'm interested in, using the dollar and then referring to the object. Okay, so that's the way it goes. Okay, so what we see here is, firstly, the first is the decomposition of the variance of the latent phenotype eroticism, shown here. So this shows you SA square to the power of 2, SA2, and SE2. And you can see what the question is now. Question is, I think, could be, what is the heritability of the latent variable neuroticism? Yeah. Now we've specified this model such that the total variance of the latent variable is equal to 1. So that means that the additive genetic variance estimated at 0.46 is automatically the heritability, the narrow sense heritability, because it's a proportion. Yeah, so 0.465, the additive term, plus 0.535, the E term, E variance, that will add up to 1, because that's inherent in the model specification. What is the heritability of neuroticism, latent variable? 0.46. Okay, what I'm also showing are the residuals, but these residuals, so the A residuals and the E residuals, these will resemble very strongly the residuals we already studied in the independent pathway model. So there's nothing new here. Okay, the last part of this practical is, believe it or not, we're going to fit a univariate model in a practical about multivariate model fitting. What we're going to do is we're going to create the sum score of the item, of the individual item. So I want to add item 1, 2, 3, 4 to create a neuroticism sum score. I do that twin 1, twin 2, do that in the MZs and the DZs. So I'm creating two new data frames, one for the MZs, one for the DZs, and the data frames contain the sum scores based on the items. Yeah, so in practice, people often administer a psychometric test, a neuroticism test, to their twins, and often they calculate the sum score and then they carry out the analysis based on the sum scores. So what we're doing here is arguably or often common practice. Yeah, so it's interesting. I want to do this because I want to compare the univariate results to the results obtained in the common pathway model. Okay, so the code to create the sum score is given. So that's simple. It's given because some of you might not be that familiar with R. So as a question in a practical, create the sum scores and the data frames. That's got nothing to do with twin modeling per se. So I don't want you to just waste your time doing that. Some of you will do it output without a problem. Some of you might have a problem doing it. I don't want to you wasting your time doing that. So that's why I give you the code so you can obtain the data frames. The first thing we do once we've done that, take a look at the summary statistics as always. Yeah. So the summary statistics, you can see that the mean is about 10, standard deviation is about 3 point something, and the correlations for the MZs and the DZs of the sum scores about 0.38 and 0.179, call it 0.18. So I'll call it 0.38, 0.18. Yeah. Okay, well, we're looking at AE model. Should we perhaps consider D before we, univariate D before we continue? Yeah, maybe you should. So you can consider that homework if you like. The fact is that 2 times the DZ correlation is about 0.36, 0.36. The MZ correlation is 0.38. It's almost the same. So I seriously doubt whether you'll be able to detect any D. As I mentioned before, if you do that test and you say D is not present, you cannot be sure that's correct. Yeah? So there could be a small amount of D that you don't have the power to detect. Okay, so the next thing we're going to do is we're going to use the univariate twin model to fit the AE model to these data. Yeah, if you're curious about the D, and if you are, then I applaud that because it's a very good question. That you don't see it on the item level analysis, does that mean that you don't see it in the sum score analysis? Who knows? But this code, the univariate model shown here, includes D, but in this model, it's a fixed parameter fixed to 0. So you could easily free that parameter up, fit an ATE model. If you want to explore that possibility, here's the code. Yeah. So let's run the univariate model, and then we'll answer the last question of this practical. Question 2.12. What is the heritability of neuroticism sum score, and why is it different from the heritability based on the common pathway model? The variance components can be obtained from the open mix output as follows, and I give you, I'll just cut and paste it. So this is the way you do it. This model, this is Hermine's code, Hermine Mass code, and she very conveniently includes open mix functions to calculate the standardized variance components. So it's part and parcel of the output, which is very convenient. I'm not very good at OpenMix, so I'm glad that I have this at my disposal. Okay, so let's take a look at the results. To answer the question, the first thing we see at the bottom, you can see the results. You can see 2 variance components, the A and the E variance components. The E variance component is 3.92. The A variance component is 3.92. The E variance component is 6.42. Yeah. So I want to know what is the standardized isogenic variance components. Add these 2 together. That will give you the phenotypic variance, and then divide the sigma A, the 3.92, by that phenotypic variance, and they'll give you the narrow sense heritability, the standardized, and the standardized variance components. The narrow sense heritability is 0.378. Okay, so what was the variance? The heritability in the common pathway model was, if I'm correct, I think 4. Let's see if I can find it. 0.465 versus 0.378. Okay, so that's quite a large difference. Why are they different? The sum score is characterized in part by the error of each item. So if you have 4 items and each item is characterized by error, if you add them up, the sum scores, it will still be characterized by error, not as much as the individual items because they're averaging out, but the sum score still has error. Okay, so That means that the sum score, the E component in the sum score analysis will include error. Yeah, but in the common pathway model, we're carrying out an AE decomposition of not the sum score, but of the latent variable. And the latent variable does not include error. Yeah, in theory at least. And you can see that I just share the workbook. Just want to show you the figure, the path diagram again. So here on the right, you can see the path diagram. The neuroticism is a latent variable. It's not characterized by error, because where is the error? We've estimated the error terms as part of the item-specific E's. Yeah, so this means that the decomposition for neuroticism as a latent variable is a decomposition of the latent variable that is corrected for any error there might be. Yeah, in the sum score analysis, the sum score neuroticism is still characterized by error. Yeah. So that concludes the practical. Common pathway model is really a powerful model because it incorporates in the twin analysis strong psychometric theory concerning the items. Yeah, and because it's a highly parsimonious model, and it's a powerful model because it combines the psychometric single common factor theory with the twin model. So that's why it's a highly attractive model. And I just show you so what am I doing? I don't know. Here we go. This is what I want to show you. So many papers have been written about this aspect of combining psychometrics with twin modeling. And there's one paper here. This is shown at bottom right, which I'm a co-author on this, so sorry for being so vain. But this is a good paper because it's discussing this issue, whether the genetic modeling within the common pathway model, does that help you to understand the dimensionality of items? Yeah. So it's an interesting subject matter, and it's been applied quite a lot. You can see this is just a selection of papers. Yeah. Okay, so that concludes the, I'll stop the share. That concludes the practical part 2. I hope all this was clear. And if you have questions, I imagine you'll know where to find me via email, if you like. And good luck. Goodbye. Thanks for attending.